are? Okay. So they did. They have, in fact, T.D. Lee may not be aware of. He gave a equilibrium solution of Euler equation, okay, which I am going to mention in the lecture at some point. So let's first start with the question, okay, which does shock a lot of people. So let me see whether it shocks you or not. If you are aware of it, then it won't shock you, but if you are not aware of it, it will shock you. Okay, so we start with diffusion equation. Okay, so I am going to use perfume as an example, and I am going to ask you, if I have a perfume, how long will it take in this room to diffuse a 1 meter distance? So can you make an estimate? Okay, so if you have not done it, let me just do the work for you. Okay, so we can estimate. So this is the perfume density. Phi is a perfume density field. You can make it continuum. It's like a smoke. It's not visible to the naked eye, but it is something like a smoke which is going around. So in turbulence we do this often, okay, because this is a exactly solvable problem, but most of them are non-linear, so you don't know how to solve them. So we try to make some division analysis. So here I can get the time scale phi by t equal to kappa, gradient is 1 by L, so L squared phi, so phi cancels, so t equal to L squared by kappa. So this is in fact this is done in math methods course, right? So L is 1 meter, so 1 meter squared. Now kappa, you particle physicists won't know about kappa, but we do it all the time. For air in a room temperature, normal pressure, this is 10 power minus 5 meters square per second. You take my word, okay? I mean, you can look it up in Wikipedia, you will find this number. Approximately, it varies with temperature. No, in fact, you can derive it from StatMech. I'll just give you a puzzle. Kappa is mean free path length multiplied by sound speed. That's it. That's how you get from StatMech. So it is not mysterious. So the time scale comes out to be 10 power 5 seconds. Okay, now if this is the case, then all the perfume industry will go bankrupt, right? Who is going to wait for 10 power 5 seconds? So something is wrong, right, in this? So what has gone wrong? Okay. Not the right equation, indeed. So what is the right equation?
Some term which is actually accelerates.
Yes. So what is that term? You are almost there.
There has to be a derivative term, I guess.
Yes. So in this air, there is a fluid component. So you can see that smoke is advected by the velocity field. We know this. And this velocity field is not the molecular velocity. Molecular velocity, we know the sound speed is 300 meters per second. Right? That's the sound speed in air. But the velocity right now in this room, velocity is moving. You can put a agarbatti or cigarette smoke, it is moving, and that speed is around. You can try, I think, as long as the organizer doesn't complain to the head. He won't complain, but so 1 meter per second, or maybe 0.1 meter, 10 centimeter, it will move in a second, right? I mean, that's you can make a guess. Well, 1 meter per second is a good estimate. So this is much faster than 1 meter per second. So the velocity is the collective motion of lot of molecules. It's not a speed of single molecule, and that is coarse grained picture. Velocity is a coarse grained picture, and that has to be included here. So the total derivative phi, not the partial derivative phi. So you put the total derivative phi, then u dot grad phi. This is the term which is advecting the perfume. Now how bigger compared to this term, how much bigger is it, this term? You can do the ratio, and it turns out to be 10, in fact UL by kappa. This is called Peckley number. Okay, there is a Reynolds number, there is a Peckley number, this is the diffusion coefficient. It is a non-dimensional number. This is 10 power 5 for atmosphere. So this term is 10 power 5 times bigger than this. So the time scale does not come from here, but comes from here. So time scale, if I want to estimate T equal to, from here you can just easily do it. I will not bore you with that. L by U. This U is not the thermal speed, but is a fluid with speed. Okay, this U. So let's not mix up this V with the sound speed. Okay, and that's why fluid dynamics is important. Okay, engineers focus all the time. Unfortunately, physicists are not interested in this. That's that's what I am trying to motivate today, that you should get interested part time. Okay, I mean, I'm saying, yeah, everybody has their own business, but you can try this, and there's lots of problems to solve, really. So this will, now L is 1 meter, U I said is 1 meter per second, this is 1 second. So this is a time scale for the perfume diffusion for a meter. We can do this analytic, we can solve this problem exactly, but this problem can't be solved exactly. It's in fact it's a non-linear problem. U is also a field which is changing in time, and that U we solve using something called Navier-Stokes equation. There are variants of it, but I'm just going to stick to this equation. So this is another equation. It's one of the most important one in engineering for sure, even in physics. I mean, as I told you, I just wonder why should we teach this in StatMech course? We should include this in StatMech course, no? But it's not. I mean, people are always, every student I asked, they say this estimate. I mean, they will basically start from here. So this is one, at least when you teach, you should include it, that component for 10 minutes. Now this equation is a Navier-Stokes equation. So in fact, it is similar to this equation. And so I think let me just make one more remark before I get here. So how is it connected with renormalization? Before we get to some calculation, it is connected with renormalization. So let me make the connection. So this is our bare viscosity or bare diffusivity, okay, which is small. This is the diffusivity kappa, which is small. Now, so that is there at the mean free path length level, but I can coarse grain now. I can do step by step. If that's what I'm going to do in my, like, I'll sketch it, the derivation for Rg. So I'm going to do this. This is the nonlinear term. So I'm going to treat that as a perturbation. So I'm going to rewrite the equation. So d by dt phi minus kappa grad square phi equal to, this goes to the right hand side, u dot grad phi, and you can put a coupling constant lambda, which is right now 1. Okay. So we do this. So this is a linear equation, which is our diffusion equation. Now I do perturbatively solve this problem. Then kappa will get correction from this term at every level. Okay. So you can derive that kappa correction at every level, and kappa in fact is function of length, whatever length, right? I mean, in your beta function there is a length, and that function, in fact we can derive it, you can just take my word for it, L 1/3 epsilon 1/3. This is the energy which is supplied by buoyancy for a smoke, you know. So this is the energy supply rate to the fluid by external sources. So this equation, this has dimension of kappa, and this is what so it's L dependent. The way charge of a particle is L dependent. Okay.
So this gives us Kolmogorov scaling?
Is derived from Kolmogorov scaling. Other way around, we can derive it. I am going to do that part in a minute. Okay. So this is the connection of renormalization, which I will sketch how to do it, how people have done it. Okay. That's what is my objective here. So there is one-to-one connection. If I just dig deeper, So the theory is free at small scale, right? This is a linear equation, is free at small scale, but when you go to larger scale, is getting renormalized. So it is similar to QCD.
So this perturbation is like this cascade.
Perturbation is coming from the effects are coming from cascade. Indeed, yes, it is coming from cascade. So QCD connection is definitely here. Third point is a non-equilibrium field theory, because there is a, I'm going to tell a little bit of non-equilibrium bit later. So let's just keep that part for in a minute. Okay. So this is the equation which we, of course, this is coupled with that U. So I need to understand that equation as well. And so this is a linear term, which is a diffusion term. So or viscous term. Okay. This is a viscous term. Now this is a nonlinear term, is coming from again total derivative, and this is a pressure gradient. So I think for today's lecture you can ignore the nitty-gritty of pressure gradient. There is a pressure, no? This is a, in fact, in atmosphere always there is a lot of pressure gradients, and that is moving the flow from here to Delhi and so on. And we have some forcing. So this force can come from like earth is stirred by the sun, or if a coffee I stir it with a spoon, no? So that, let's take the coffee as an example. I always stir it, I supply energy at large scale, and that cascades to small scales. Okay. So I am just going to discuss that part qualitatively. Okay. Today don't expect me to get it well. I mean, it will bore you. There are detailed calculations. Some of it is very rigorous, but I am just going to make it qualitative. And we assume for this talk the flow is incompressible. That means the density does not change with space and time. So that's an assumption which doesn't work in astrophysics, but for water it's a good approximation. Now this equation biggies have tried with some success, but mostly failures. Okay. Like Heisenberg did try this. His thesis was on turbulence. Werner Heisenberg, okay, quantum mechanics. But the best theory we know is Kolmogorov's theory. Okay. So I am just going to state Kolmogorov's theory. Okay. State the result, then try to derive phi-third that kind of relation. Okay. So Kolmogorov proved this is a analytical theory. Okay. Under some mathematics assumptions. Okay, it's not a physics assumption. He did derive it. The papers are very short. In fact, you can read them quite easily. Is there in the PDFs are available now. I mean, rather, English version is available. It's 1941, written in 1941 in the Russian journal. Okay, DOKL. So I can give the reference. Maybe I'll send you the review paper which has the reference. Okay, so what Kolmogorov proved for homogeneous and isotropic. Okay. Now a coffee when it's stirred with spoon is not homogeneous and isotropic at all scales. Well, I think where some connection with CFT can come. I know very little about conformal field theory. There is one paper by Polikov. That's the only thing I am aware of for 2D turbulence. But this one, the fluid coffee cup especially is, you can say, is like there are large scale vortex and there is a cup boundary. So it is not isotropic and homogeneous. But if you go to small scales, something like a centimeter or so in a cup to a millimeter, this is isotropic and homogeneity. So it depends on the scale. So that's what we call L, much bigger than the mean free path length. Right now I am just on a mean free path length, but much smaller than the box size. The system is homogeneous and isotropic. Now we can take 2 points in that fluid in that regime and take the velocity difference between the 2 points. So I am just going to say ux plus L minus ux and dot product that with L hat. So this is L vector. So dot with L. Okay. So n ensemble average. So these are scalar. I do cube n ensemble average. This is minus 4 by 5 epsilon L. Epsilon is the energy supplied by the spoon. You know, I stirred it, I supplied energy per unit time, energy supplied per unit time to the fluid. Now I am going to make density is 1. So epsilon has dimension of u squared by t, energy by time. Okay. So there is no density. So it is will make mass go away for this problem. So this is what he derived is exact under this approximation and viscosity going to 0 limit. So we assume the viscosity goes to 0, fluid is steady, that is another assumption. So you have to keep stirring all the time to keep maintaining it steady. Now this is cubic, so you can easily, well not easily, that is where this is exact. But now somebody may say, well, I am going to call it delta u squared. What is this quantity? So in fact Kolmogorov himself argued delta u squared should be, this cube is L, so delta this should be 2 by 3. Okay, it's a scalar quantity and epsilon 2/3. It turns out this is not correct. There is a small correction to 2/3 which has been measured. To 2/3 is 0.66, but this number is 0.71. There are very good experiments and simulation. This number is slightly above 0.66. Very high resolution, like lot of supercomputing time goes into this, and they found it to be slightly bigger, and that is connected to intermittency correction. So it turns out this is exactly solvable, but somebody may say, well, what happens to q? So you may say q by 3, L q by 3, epsilon q/3. This is not correct because it is not a simple fractal. It turns out to be fractal. It's called multifractal. Okay, so the structures are not homogeneous. They are fractals in the sense they are structures within structures. I think that is connected with conformal field theory, that there are structures within structures, but the structures are not homogeneous to whole volume. Some are more intense, some are less intense. The story goes that Landau made that objection for the first time. It's not clear, but people say in a seminar when Kolmogorov was talking, he said, well, this is not correct. Well, here implicitly it was assumed by Kolmogorov. Well, I mean, I think some of these seminars are now people understand partly, then there is the question, but it leads to very important discoveries. So dissipation is strongest at the point where vorticity is strongest. So in this room itself there are places where vorticity is strong, like hurricanes, small hurricanes are there in fluid, and they are not uniformly distributed. It turns out the infrared is singular. There are few places the intensity is very strong. So dissipation is not homogeneous everywhere, and that is not a uniform function in the whole bulk, but it is concentrated in some regions where it is very strong, and that leads to this correction of 0.71. So maybe that is one problem, I think, which has not been solved. We know solution for cube, but not for q other than 3. Okay. So I think people are tried. Prokachya is one name, I think, who probably the high energy people may know, Itamar Prokachya. So he did try it, but no success. Anyway, so now, so this is squared is, and that formula looks like this, right? So this is, so how do I get the diffusion coefficient? So I think I made a mistake. This is there is a mistake I made. So this is minus 4/3. Okay, this is minus 4/3. Kappa is minus 4/3. So now let's do division analysis and try to derive diffusion coefficient at different scale, and which will be useful when I discuss this RG part. So the velocity at length scale L is epsilon 1/3, L 1/3. This turns out to be pretty good approximation, all this scaling argument. So what is the renormalized viscosity? I think, I believe some of it is done in high energy as well. So you can do dimensional analysis and try to get this stuff. So the So L 1/3 actually is plus 4/3, okay, not minus plus 4/3. So now my dimension is this dimensional analysis, the kappa or viscosity at length L. So viscosity dimension we saw velocity times length, mean free path length times sound speed. So the viscosity at different scales are UL multiplied by L. L is the length scale, it is a scale invariant system. So there are vortex within vortex. There is vortex here, there is vortex here, vortex here. Then within that there is vortex. So unfortunately I don't have a good picture in my slides, but you can easily do Google and find images turbulent flow, and you will find vortex within vortex. So this one now you can see epsilon 1/3, L 4/3. So these are renormal viscosity for Navier-Stokes equation from dimensional analysis. An idea is to, well, there is a coefficient in front nu star, which is a dimensionless constant, and lot of attempts are made to compute this coefficient, which are useful for engineering because we want to model atmosphere, and our simulations can't really go from 6,000 kilometers to centimeter. So you need to model the small scales, and that's where this nu star plays a big role. Okay. Anyway, this is a Kolmogorov theory, this part, and this part is extrapolation from Kolmogorov theory. There are lots of things we can talk about. This one example, well, this one offshoot of Kolmogorov's derivation. So any questions so far, if you have any? Okay. So turbulent diffusion I already talked about, and now let's go to Green's function and path integral. So one question, well, you are working with differential equation, but we do quantum field theory using path integrals, right? So is there a, I mean, what should I do? Should I try to derive Hamiltonian for fluid mechanics or Lagrangian, right? I mean, that's a one bottleneck. Any student will say, well, no, I don't like this because it doesn't have Hamiltonian. But we don't really need Hamiltonian. In fact, this has been told before. So this was of course I taught tapestry of field theory. Okay, so I was trying to cover broadly various topics. So for this equation, diffusion equation, this is we can derive the Green's function, which is this. This is exactly derivable. I mean, this is like probably done 100 years back. But Feynman path integral is exactly this. So I am going to convert that to Schrodinger equation. So instead of and Schrodinger equation is, well, I mean, this in fact has a very similar structure. No, you put I there in diffusion equation, I get a Schrodinger equation, I h bar dy dt, right? So put I, and then you get, well, sorry, this is not diffusion equation. Without I is a diffusion equation. There is a minus sign. But to derive Schrodinger equation Green's function, you just have to manipulate a bit, and it's the same function. So the Green's function, this is a simple example, is basically the Feynman path integral. Okay, so he is doing by some other method, but the result is the same. So what we do is identical. There is nothing. So it's just that which method you use, and this is for free theory. Now the problem is to compute Green's function for interacting theory. Okay, and my interaction I told you is u dot grad phi, for which I can't write Hamiltonian or Lagrangian, unfortunately. Okay, but there are people who have tried it. I am going to give some reference. So there is a like Kildis formalism. Okay, that's formalism through which this has been tried, and I think I am going to mention some of that problem which everybody is facing. Okay, and some people said, well, I will ignore the problem, but I get the result, and that too is somewhat successful. Okay, so now let's get to the brass tacks and do some calculation. Okay, so I am going to do briefly two calculations. Okay, so there is one is like a Dyson-Swinger equation. This was done by Creighton. So this name I think I am going to also put on board. After Kolmogorov in theory of turbulence, a name which comes is Robert Creighton. So he did this field theory in 1959. Okay, this is our like not even I was not also born that year. So these are like 100-year-old kind of work. So 1959 he wrote this paper, and if you see that it is kind of Dyson swinger. Okay, so I'm not going to follow Krignan's notation. Krignan's paper is long and bit like complicated, but let's try to see. So I'm talking to particle physicists, so I want to convert that language. So this is there in this paper which is going to appear soon in the Namo Cemento La Ravida. So this is a review article. Okay, I'm going to send it to Pratim and he can forward it to you all. So this is there in that. I just copied from there. Okay. So we rewrite that equation. So first, let's go to one more point. So what are the parameters of the problem? So we have one parameter which is viscosity. Okay, that is, you can see now. I'm trying to make the connection. It's like mass, right? It's a linear term. So Lagrangian. Now I learned that part. So it's for phi 4 theory phi squared, then we have m squared phi squared, and plus lambda phi 4. There is a r there, right? Minus plus. So I don't know what you guys choose, but I learned from Wilson phi 4 theory. That's a Lagrangian. So this m squared is a linear term, that is like viscosity. Okay, of course, it's not well. This is basically the connection.
First term is height.
No, sorry, grad phi. No, yeah. So m squared. No, this m squared. So this m squared. This m squared, and this is grad phi squared. So this is a kinetic term, and this is the potential. These two are potential terms, right? I mean linear and I'm sorry, I was making a mistake. Okay, so here, so that is the linear term. This is a nonlinear term like lambda phi 4, this one, but the nonlinearity is of different sort. And if you are doing dynamical field theory, so one thing is in Wilson theory this is not there. You can do redenomination group, omega is absent. So there is a heat bath, and the system is there in heat bath, so no time dependence. But we put in time dependence, so system is, so let me just tell you what is non-equilibrium in this. Here there is energy cascade, right, which we discussed for Kolmogorov theory, there is energy cascade. That is non-equilibrium because detail balance is broken. Energy goes from large scale to small scale. If system was in equilibrium, then there won't be any transfer. Equilibrium guys like, well, nobody is a Russian any communist system. Okay, there is basically everybody is equal energy, equal money, no transfer. You just trade food and basic stuff. Okay, but non-equilibrium is like American system where there is very rich guys and there is a transfer. So this is what is happens in non-equilibrium. Okay, so unfortunately, world seems to be non-equilibrium, at least economically too. So this is what cascade is around, and that cascade requires that we have this frequency part included, and forcing is also included. In this system with large variation in scales, so energy goes at comes in large scale, and there is a dissipation at small scale. So I can imagine poor people at small scale and rich people at large scale, and there is a cascade of money flow. In fact, that analogy seems to be okay. I wrote a paper on that one, so you can try to see what kind of power law is there in wealth distribution. So I do believe there is some kind of cascade of money in economics too. In any case, we don't go there. So here this one parameter is new, other parameter is lambda, and third parameter comes from forcing. So I am going to make some model for the forcing. Okay, and this is a non-equilibrium because the detail balance is broken. Now we do perturbatively, the way is done in field theory. So we replace U by perturbation series, and I am going to plug that in. Okay, and I am going to follow Wilson RG, wave number RG from the differential equation. So the nonlinear term is written like this. So there is a product, right? U dot grad U. So that's a product. This is a tensor coming from gradient. But I believe right now just ignore all the indices. It's not important. just see what is the core objective. So this is a non-linear term. So now I am putting u00, so this is the first order or 0th order, then this is the first order and this is second order and so on. Products, all sorts will come, and this is force. Now Baire-Green's function is basically, this is inverse of Baire-Green's function, linear term, no? So this is G0. Now my correlation function is a 2-point correlation. These are indices, so you need to, don't worry about it. UU is a correlation function C. Now turns out, now these are detailed part, to 0th order this is 0, this has no contribution to this, to the integral. We have contribution comes the first term, and we can write the Feynman diagram for that, or expand it. No, first term I want to solve this one. So what do I do with U1? U1 is solved using Green's function, right? So U1 will be, so G naught inverse U1. So we get equation like this, U1. The right hand side will be previous order, U0, U0 and lambda. So U1 is Green's function, G naught and U0, U0. This is what I am going to get from the for U1. So that is the Feynman diagram which I have it here. So I have two U's like that. So I am going to replace one U by Green's function and two U's. So instead of writing the, in fact Feynman, in fact it is a great contribution, well his great tool is, you can easily write the perturbation series. Now I am going to contract this. So these two together I will combine them. So that is a correlation function, and this is a Green's function sitting here, and one U is outside. One U is not averaged. So that U, so what does it give us? This is a hanging guy out there. So let us look at the previous slide. So this term is giving us something proportional to U1, proportional to velocity. So this is the term which is proportional to U, so I can take it to the left hand side and correct the viscosity. So I hope I am getting myself clear. So this term is proportional to velocity. So that is what is correcting this this viscosity. So that is the idea of, for here. So I get this. This is a loop diagram which is correcting the viscosity, or your mass correction. No, mass correction is or charge correction is the loop. This is the loop, and that loop is here. Correlation function. Well, I mean this correlation function, Green's function. So that is the analogy. In fact, is exactly same, except these are classical fields. So I don't need to worry about Wick's theorem and so on. I just had to do it. Well, there is a connected Wick's theorem, but these are not operators. Now it's time dependent, so I need to assume something for Green's function, correlation function, and these are time dependent. Unlike equilibrium field theory, they are only function of k, no time. Okay, so you plug all that in and you get basically the new star. So you get something for Green's function, time dependent Green's function. The idea is to derive this nu k, which was what I have, nu k or nu L, that is the idea, which Kriegman, that paper has problems. In fact, he didn't get the right answer, but that's where he led this movement, you know. People started working on this problem after that. So, basically, this there is a slide. So this is Dyson equation. No, so this is my full Green's function here. The full Green's function, because nu k is normalized. You agree with that G inverse? I mean, this is a full Green's function inverse, and that is connected with this integral, which is self energy. So of course this has also infinity problem, at the infrared infinity is there in this integral. Okay, so there are some corrections. Well, basically you put a cutoff. I think I'm not really an expert. The QED, I look at this book, there's too many indices and so on. the translation is I am lost. Okay, so that's where you guys are experts. If you can translate it, this is what will lead to. I think there is a one-to-one connection, and there is a infrared cutoff. I can show you. We can work that out fully. Now, so if there is any question, I'll be happy to answer.
Sorry. You said that it's a low momentum divergence in this interval.
Yes, there is a 0 to infinity for Q, and at lower number there is a divergence. Not at infinity. Here there is a no problem at large thing, but low there is a divergence.
Shouldn't there be a cutoff of biases? This description will be valid up to a certain let's take as in have to put a cutoff.
Yes, so that's how people try to solve the problem. There is a cutoff, but cutoff, if you put a just constant cutoff, then you don't get 5/3. This is a cutoff which is k dependent cutoff.
Yeah, but at the end of the day, absolute description is an effective description. So there has to be a ultraviolet cutoff at which.
Yes. So that cutoff is put, but cutoff has to be properly put to solve the problem. But one more point. So like Kolmogorov theory assumed that my viscosity is 0, tending to 0.
Yeah.
So my cutoff is at infinity. My low wave number cutoff, or sorry, high wave number cutoff. Viscosity 0 means the smallest fluid scale is very tiny. In fact, it goes to 0. So, like ideal theory, Feynman, what he was trying to do, he was saying that let it go to infinity, both sides. That's what we want to do it here too. This sending to infinity is not a problem, but sending this to 0 is a problem. But there are ways to sort it out. RG is one very good step to sort it out, which I am going to tell right now. So Kretin in fact went away from this called Eulerian field theory, where I am not using particles at all. He made a mistake, and he said, well, all this field theory is wrong. So in fact he moved away from Eulerian to Lagrangian, which really did harm to the true field theory efforts. But this guy called Leslie, who has a book, he doesn't have paper, but in the book he says the lowest cutoff K0 is lambda times K. Not lambda, let's call it alpha times K. Lambda is a coupling constant, alpha times K, and this alpha is a constant. If you put it, then you get 5/3. But somebody may say, why are you choosing this cutoff? This looks a pretty weird cutoff. It should be just some number, no? This is just this K0. You put K0, then I get K minus 3/2, not 5/3. Okay. So these are issues which requires. We understand somewhat why it is so, but I will not get into that. Okay. And now let's look at the next step is Jacob-Orzog procedure.
Sorry.
Yes, please.
I understand this is non-relativistic, but why the cutoff, why the divergence is at 0 momentum and there is like here in relativistic UV it's usually from the UV that causes.
Okay. Okay.
So how to see, is there a way to see this?
Okay. First of all, this is a non-equilibrium. So let me make a remark. For the equilibrium part, so this is a non-equilibrium and the spectrum is K minus 5/3. Okay, so it's pretty steep spectrum, and you can see that it is K minus 5/3. So this guy is going to do something at small wave numbers, right? It's a power law, K to power minus alpha, and alpha is positive. So the small wave number divergence is coming because the energy is going increasing rapidly with small wave numbers. Equilibrium field theory is no problem in this. Equilibrium field theory is called Eulerian field theory. So let me make a remark. Eulerian field theory assumes that, well, not assume, in fact I can show that the energy of each mode is equal, that's a communist system, and the energy is k to the power d minus 1 for the spectrum, and that has no problem either ways. In fact, that's easy to do. So it's a non-equilibrium feature which is causing trouble. So you should really connect with some non-equilibrium QED if you want to connect that divergence, small wave number divergence, I think. But I'm not an expert, so you guys should get into it and try to see whether you can get a good answer for that problem. So these are some issues which I think right now in turbulence there were people who are doing field theory, but there is no funding at all. Okay, for so people are doing biofluids or engineering fluids or atmospheric this atmospheric fluids, and so there is nobody who is field theory there is basically nobody right now except a convert from string theory to Vladimir Rosenhaus. He is doing field theory. So these are people who are kind of who are trying to explore. Okay, so anyway, so this is one. So let me just quickly now. My time is going finishing. So Jakob Orzog, I am going to just say. So this is 1986. So 1986, we have three parameters. I said nu, lambda, and this D is coming from the force correlation. So you might, so there's one work which got lot of attention is KPZ. Yes.
The L that you had here.
Yes. Right.
Does it correspond to the alpha or the no momentum or the?
No. This is no. This L is corresponds to lambda by. So here this Wilson RG. No. So this is Kn plus 1. This ratio. So this ratio Kn plus 1 by Kn is e to the power L. So this is the usual in what is called beta function. So that L. So this L, yeah. So I should warn you that this L is not same as length scale over there. So the notation is an issue. So this L is not the length, but it is that what you have for your beta function or gamma beta function basically, that ratio of these two numbers. It's exactly same with Wilson RG, and so this is there in particle physics. I have seen you get these two equations because there is no forcing. This equation is absent, and so this is the term which is coming from nonlinearity. Now one more point which I learnt, the QED is also a nonlinear theory. Okay, would you agree with me? Because it's the matter field is interacting with the electromagnetic field. So that interaction is u dot grad u for me, or u dot grad psi there, and that correction is basically this correction which comes from bubble diagram. This is a bubble diagram, and lambda, it turns out because of Galilean invariance it doesn't get corrected. So that's a strange part. This is lambda, this coupling constant for the nonlinear term is unchanged because of Galilean invariance. I will not tell you the proof, but is there in the review. It's pretty straightforward. But this is not the non-dimensional coupling constant, or not. It's not really the real coupling constant. Real coupling constant is this. So AD is that integral. So epsilon is connected with energy injection rate. So this what is derived in Jakob Orzog. So this is important. This is that E squared by h bar c should be compared with that, because that is part of that the series expansion. You will find lambda bar in this paper. So this is order 1, by the way, because epsilon is order 1, a non-dimensional energy supply rate, and so this is order 1. Now that's another problem which like Vladimir, I met him in Japan 2 weeks back. So if coupling quantity is order 1, then say, well, perturbation theory breaks down, and we should not apply perturbation to this. But in turbulence we say, well, let's still apply and let's get some answer. Okay, and so that's what has been done. So this guy say, well, even though it's order 1, I'm going to apply, and I'll try to get an answer. It turns out that the epsilon expansion, there is a expansion, epsilon expansion like 5-4 theory. Epsilon is 4, not 1, to 4. Okay, and that's another problem. Epsilon 4 for Kolmogorov theory, I need epsilon 4 to get Kolmogorov spectrum. So basically, yes. So this is these are the flow equations, and from flow equation I get this coupling constant, which is this, and for y, so I will get this X spectrum which is function of d, a function of y. D is a space dimension, by the way. This D you will see the space dimension. I will say let's put 3, but energy depends on y. Now I skipped this because I really didn't want to get into detailed derivation. You can derive a spectrum, which is function of y. Now I want phi third, then y has to be equal to the space dimension. Okay, this was done by these guys, and so and that leads to epsilon equal to 4. Okay, and somebody said, well, epsilon equal to 4 is garbage, but that's where we are in this formalism. Yes, please.
In field theory, there is this expansion in around for some non-unitary models that does 6 minus epsilon. People put epsilon equals 4 a lot.
Oh, really?
For that one, it works reasonably well.
I see.
But it's that the expansion has nice properties, so it still converges down to epsilon 4, but it's a very specific example.
I see. Okay, I like to get the reference, and yeah, so right.
So you are trying to look for a theory where you get Kolmogorov scaling throughout.
Yes.
So normally I would have expected there will be a bound on the wave numbers, and the range in the wave numbers.
Right,
where
right.
I would get Kolmogorov scaling and to break in the other domain.
Right, right, right.
So is there a way to get a upper and lower bound in which this might be correct and not be correct?
So that is
This is a multi-scale problem, so it's very unlikely that Kolmogorov scaling sort of holds throughout.
so we are focusing on the power law regime. So if you want
What I'm
to,
asking is, so where is the information that you are focusing at a particular regime?
so here I am looking at power law regime, and it doesn't know the box size and doesn't know the viscosity. Okay, so in this stuff, I am supposed to be, this is a box size k naught, inverse is box size, and I want to stick somewhere here, like Wilson 5-4 theory.
No,
Is-
after the box, I was saying that even in the wave numbers.
No, wave number in the power law regime, it is scale invariant. It's a scale invariant. That part is scale invariant. There is no box size is not going in there. So a Kolmogorov theory is k minus phi third. Okay, let me just write it here. Epsilon 2/3 k minus phi third. This has no box information and viscosity information. That's in fact that's purely universal theory. It has.
That I understand.
Yes.
That's a very good dimensional analysis thing.
Actually, no. By the way, field theory also gives the same stuff. That's the beauty of field theory. All these guys wanted to derive Kolmogorov power law from basic principles. So that's the attempt. It's like as rigorous as what QED is wanting to derive the coupling constants from first principles. So that's the attempt, and I think it is as courageous attempt. So there are caveats or there are assumptions which do not seem proper, and that's where people don't say, well, we not solve the problem. Okay, and this is for the second order, basically spectrum. Higher order correlations, we need diagrams which are more loops and so on. I'm not an expert of that, but it has not worked well. Now the next question is, I just want to end with that. So you can also compute energy flux. Okay, so energy flux is told it is non-zero, and how much energy flows from large scale to small scale. So I just going to write the diagram, and I think it's also, I believe, I am to my Stanford friend, we got to know each other, and the thing which field theories don't try is energy transfers, because things are mostly in equilibrium or near equilibrium. Near equilibrium also you can ignore how energy is flowing, but I am saying most of the problems in the real world are, at least what I see, is driven non-equilibrium with lots of energy cascades. I believe even the early universe is huge amount of energy is cascading over scales. So how to compute energy cascade, and that guy at least is very interested. Okay, we should do this part for quantum turbulence in condensed matter too. So let me just tell what the problem is, and I think this, some of you may be interested in this. This is, I think, doable. This doesn't have any divergence problem, by the way. It turns out it's a very doable problem. So we can write down the equation for the energy in a Fourier space. So I wrote the equation for dy dt of u of k, and the right hand side was up and uq, right? So this is coming from u dot grad u. So I multiply this by u star of k and take the real part. Okay. So I'm basically, believe me, that equation for the energy equal to 3 U's, UP, UQ, UK. Okay, these are nonlinear term. Now the energy here will change because of nonlinearity. Now I can get the number. So to 0, if I assume Gaussian, which is done by most of the field theory, including high energy field theory, this is 0. If I assume Gaussian, Wick's theorem 0. So I need to go to next order. So how do I go to next order? So I have this 3 U's, 3 U, U, U. Then I go to next order, just take one of them, Green's function and 2 more lines and 2 lines here. Right? So this is the first order perturbation. This is, you guys do like in your sleep. So we can connect this here and connect this here. So we have integral involving 2 correlation functions Cp, Cq and Green's function g of k. So this is the integral which we have to do dp and q is k minus. So this is the integral we need to do. And this integral is finite and positive for 3D. So this connected with energy transfer analytically. I get a constant flux if I put Kolmogorov theory in there. Okay. So this is done by Crichton first time in 1959, the same paper, and we get a finite number if I put in phi third. Now imagine I put k squared, that Eulerian, what do I get? Intrinsically, if I put this spectrum to be k squared for 3D, I get 0 flux because it is equilibrium, no flux. So no cascade and it's 0. So I think this is what we want to do for quantum turbulence, which is with wave function, Gauss-Petrovsky, and compute them.
But what did you say you were asking?
Yes.
Quantum turbulence is no. This is only a domain wave number when you actually have height.
Yes, yes.
Beyond that, there's an expansion.
I agree. So quantum turbulence, yes, there are k minus 1 scaling, k minus phi third scaling. I know. So we'll see flux in that regime.
Right.
And yeah, so integral may be an issue there, but we'll see. Yes. Okay, so I think I'll end here. I'm over late. It's already 10:30. I start. Oh, I see. I guess people, too much information has gone in. So let's keep it question answer. Okay, you may have. So let me just summarize. Okay, so here renormalization has been attempted. Overall, I would say there are 20 papers. Well known are only 4 or 5 papers in turbulence, and you can see the sketch. It is non-equilibrium correction. So we have 3 viscosity, coupling constant, and the diffusion d, and we try to compute them. It works okay. Well, I mean you have to be happy with epsilon equal to 4 and all that stuff, but this the form that epsilon 1/3 L 4/3 will come from the theory. So I think it's good actually. In fact, to me, I believe. Well, I'm going to give an example a bit later. Okay, so this one object is the renormalization is partially successful. Yes. So RG calculation coefficient is there in my review paper. So the integral gives you a nu star. You have to just juggle with the formulas and so on. Nu star comes is 0.4 roughly for 3D. It agrees well with simulations. Yes. Well, simulations are hard to get the nu star, but it's yeah, people are happy with nu star 0.4. We get reasonably good simulation. It's called large eddy simulations. Okay, that works well with nu star is 0.4. So that's one. Second, there is equilibrium theory, which is Euler equation with viscosity 0, and there is non-equilibrium theory. So equilibrium is similar to what we do for 5/4 theory and so on. By the way, Wilson 5/4 theory, omega is absent. So if you put in omega, then this model A, model B, coarsening, all that part comes in, and that requires non-equilibrium forcing. So KPZ in that class. KPZ is a special one, but anyway, I'll just say that these are non-equilibrium. And third is this energy transfers. Like I find even people who do StatMech, this KPZ, Model A, Model B, they do not focus on energy transfer. I think that's where the whole field is empty. I think there's no work, and I think this is where I think I believe some of you should try that. It's really open, and I think you can get very good results if you attempt some of these problems. And yeah, so I think that's my summary. So let me just tell you what this. I think the string, people say that divergence series is done often, but my poor man's divergence series is this. I was trying to make sense, and I'm not dug into it. I know Hardy and Ramanujam have worked on this stuff. So my divergence series analogy is very simple. Okay. So I want to solve this equation x equal to 1 plus ax. You guys might have seen this example, but this I cooked it up when I was trying to convince myself. So exact solution is x equal to 1 divided by 1 minus a. Exact solution. But I want to do it perturbatively. So perturbation is, assume a to be small. Assume a is small. That I had to assume. So then x equal to 1 to first order. Then what is the next order? I say, well, a is small, so I put x equal to 1 here, u0 or x0. Then I get 1 plus a. Then next order, I put that in here, then I get 1 plus a squared. I keep doing this. So I get a geometric series, which is, well, I mean, this has approximate, but geometric series has an exact solution. Well, can be summed for a small, which is same as this result. So we are getting the exact answer, assuming a to be small, which is also good for a large or any a. Maybe something is happening here like that for turbulence. Now, suppose that this is analytical continuation is, we'll explain this. I don't know. I mean, I don't know enough complex variables to say that this procedure is legitimate. I see. I see. So this is legitimate. Okay, so just give me a reference where this is legitimate. Then so if it is legitimate, then why are people objecting to coupling constant being order 1, and then you say you can't do perturbation? You can say, well, maybe, well, there is no guarantee it is a good result, but you can't rule it out. I mean, it may give us a. So QCD, why QCD can't do this and say, well, maybe we are trying.
I think the objection is that in this example, you have resummed the entire series, right? And when you get the function, you cannot do that in most field theories, and then you have a like if you resum the entire thing, then I think it's much more.
Those are much more difficult divergence series.
I see.
But Feynman, so one is actually people do write series solutions for Feynman divergence.
I see. Okay. So Dyson equation is something similar to that one basically, but you still say that coupling constant has to be less than 1. Maybe we should discuss over lunch. So give me a reference where you can put more weight on that that stuff.
Sometimes there's this other problem where the function is actually not analytic, so you can do the perturbation theory, but there are terms that you cannot capture, like
right.
e to the minus 1 over a. You cannot capture all the derivatives.
Right.
That can also happen.
Similar. Yeah, that's true. Yes. So, okay, any questions or? Okay. Okay, thanks. Thank you.
I think this should